Don't trash, calibrating differential charge accelerometers. Again, my name is Mike Scott. I am the Industrial Product Manager at the Modal Shop. This is the second in our winter spring 2021 series of webinars for the industrial market. Last week, I presented on a rather disruptive technology, a digital accelerometer that turns your phone into a vibration analyzer. If you missed it, it is on our YouTube channel, of course. And if you send us an email or let us know in the chat, Emily can send you a link to that recording. Next week, we will have liquid level sensors on February 4th. February 11th, we'll talk about combustion dynamics. February 18th is wireless vibration monitoring. February 25th is 4 to 20 milliamp vibration transmitters that plug in directly to your DCS. And March 4th, I'll be back with vibration analyzer calibration webinars. So hope you consider attending some of our future webinars as well. Now, you may have come here through a couple different ways. You might have been invited by PCB Piezotronics, or you may have been invited from the Modal Shop, or you may have just stumbled across us in Google. So for those that are not familiar with the Modal Shop, we're located in Cincinnati, Ohio. And if you're a customer of PCB, familiar with PCB Piezotronics in Buffalo, best way for me to explain it, like the simplest way, is to just say the Modal Shop is like the calibration division of PCB Piezotronics. People sometimes hate when I say that, but that's the easiest way to explain it. The Modal Shop manufactures all of the calibration systems that are used in PCB's manufacturing facilities. And we also provide those systems to end users in the market that have a lot of accelerometers. We also provide a portable vibration calibrator that's specific to the industrial market, very popular within the industrial market. Aside from calibration systems and services, we do rent PCB Piezotronics equipment, and we have some other divisions as well, non-destructive testing and structural test products, shakers for modal analysis, as the name would imply. If you're familiar with Modal Shop, but not PCB, this is PCB. It is located just outside of Buffalo, New York. I spent the first 10 years of my career there. And PCB Piezotronics is the largest, or one of the largest. I think we can say that PCB is the largest, but not 100% sure. It is certainly one of the largest manufacturers, if not the largest, of piezoelectric vibration, instrumentation, accelerometers, pressure sensors, force sensors, etc., microphones, should say. It's vertically integrated manufacturing facility. When I started at PCB, this building did not exist. I started in 2005, and this area here was called the Wine Merchants, which was fun, but it didn't last. They used to sell wholesale wine, and now this building is a brand new building. The Wine Merchants building is gone, not that anyone cares. And it's a 3 shifts machine shop that runs 24 hours a day, manufacturing the housings for the piezoelectric instrumentation that is made over here. And in North Carolina, there's another manufacturing facility in Halifax, North Carolina. So PCB, again, a very large manufacturer of piezoelectric vibration sensors, and specific for power gen, they manufacture high temp dynamic pressure sensors and accelerometers that go on gas turbines. Now 10 years at PCB, and I'm the industrial product manager for the Modal Shop, and passed the Cat 2 exam a long time ago through the Vibration Institute. Those of you that have attended these webinars regularly have heard all of my fun facts, so I'll just mention that this is the first time, this is, I think, my 5th webinar in the series, but it's the first one that I've done from home. Unfortunately, I have to do this one from home, so which is not ideal. So if you hear meowing, I have 2 cats. If you hear birds chirping, that's a cat toy. And my cats almost instinctively know when I'm doing a webinar for like hundreds of people. So I'm sure one of them is going to try to jump in front of the camera at some point. I'll try to just keep going. But I will be hassled by cats today in this home webinar. So let's get into the technical content. PCB and the Modal Shop have a lot to offer the power generation market. We are known for our vibration sensors, but some of the stuff on this slide is our best kept secrets. The portable vibration calibrator is used for proximity probe troubleshooting, and we don't manufacture proximity probes, so that's like a different kind of customer base for us. It's also used for vibration monitoring, system verification. We offer ground fault detection systems for brushless generators that will detect when stray current is going to cause damage to the windings of the generator. We have instrumentation for combustion dynamics, pressure, make sure that the gas turbines are running lean and have low emissions. We have industrial hygiene products for noise exposure, and we have slow speed vibration monitoring equipment that's popular in the hydropower market. So what are charge mode accelerometers? Charge mode accelerometers are the types of accelerometers used on gas turbines, and the subject of today's presentation, how to troubleshoot these accelerometers. So let's just start with what are they? Well, there are two types of piezoelectric accelerometers. There's integrated circuit piezoelectric, or ICP. That is, I'd say, the more popular sensor type because it's more universal. So PCB, Piezotronics, manufactures a lot of ICP sensors. And in that case, the microelectronics are inside the sensor housing, converting the charge output from the crystal into a readable voltage output. And then there are charge mode accelerometers that do not have any internal microelectronics. And the reason for that is heat. So the charge mode accelerometers produce raw, I say raw, that's not really a technical term, but it's kind of how I describe it, high impedance electrical current that's measured in picocoulombs coming off the crystal stack. And there's no microelectronics on the inside to convert that to a measurable voltage. There is an external charge amplifier that would convert the output from picocoulombs to a measurable signal in either millivolts or microamps. Now, why are the microelectronics outside the housing? Well, the microelectronics quite simply can't survive the heat of a gas turbine. A typical ICP accelerometer with microelectronics inside of it can survive to 250 Fahrenheit or 121 degrees Celsius. And a high temp ICP with special microelectronics can push you to about 325 or 162 Celsius. That is not high enough to survive on a gas turbine. So charge mode accelerometers are used in high temperature applications. And some of our charge mode accelerometers for gas turbines are built to survive up to 650 degrees Celsius. The microelectronics are outside the housing, downstream from the measurement in a lower temperature area. And of course, they convert the signal from picocoulombs to either millivolts or microamps, depending upon the charge amplifier that is used. Why now? Okay, so there's two types of piezoelectric accelerometers: integrated circuit piezoelectric and charge. Now, specifically for gas turbines, why are the sensors differential charge? Because there's two ways to make a charge accelerometer. You could go with a single-ended charge accelerometer, or you can go with a differential charge accelerometer. And the answer to that is common mode noise rejection. Charge accelerometers are very susceptible to noise. As I mentioned, it's a high impedance output, so it's very susceptible to electrical interference. And if we utilized a single-ended output on a gas turbine, you would get a lot of noise in the signal, which wouldn't be very useful. So we can't really use a single-ended output in a high-temp gas turbine application. We have to go with with differential. And we can't really get rid of the noise. Like one way to protect the crystal stack from the noise is to off ground it. Okay, so a lot of vibration sensors, like all of the industrial ICP sensors that PCB offers, are off grounded. Case isolated is another word for that. And the sensing element is off ground. Unfortunately, none of the materials that we use to off ground the sensing element can survive the temperatures. So we have to figure out how to handle the noise in a different way. And if we can't isolate the crystal stack from the noise, then we're going to have to figure out how to cancel it out. And that's what differential charge sensors do. On a single-ended charge sensor, there's just one, well, there's two leads, but the negative lead gets taken to ground, and you just use the positive lead. In differential charge sensors, there's a positive and a negative lead connected to opposite sides of the crystal stack. In-phase common mode noise is going to exist in this application, and it's going to appear on both lines, and it can come off the surface of the gas turbine, and it can also come through the air, like electrostatic discharge or EMI. The good news is this noise is in phase, and it appears on both lines. I know this is getting kind of electrically, if that's even a word, but it's an in-phase noise that appears on both lines. And the simple way to explain it is we're going to measure the difference between the signals on the positive line and the negative line to produce our vibration measurement. The noise, because it's in phase, is going to appear on both lines, and it's going to cancel out in that measurement. We're looking at the positive and the negative, and we're taking the difference between the two. And since the same noise exists on both lines, it cancels out in the equation. The vibration signals are out of phase, or 180 degrees out of phase. When the sensor moves up, the signal from the positive lead goes up, signal from the negative lead goes down, and vice versa. So we're able to measure just the vibration and cancel out the noise because the vibration's out of phase, 180 degrees out of phase on both lines, and the noise is in phase on both lines. And so that, in hopefully a not too confusing nutshell, is how a differential charge accelerometer works, or any differential accelerometer, by measuring the difference in the signal between the two lines and canceling out the noise by doing so. This is a typical high temperature differential accelerometer system. Accelerometer shown on the left with an output in picocoulombs per G. A lot of these sensors have integral cable to flying leads, so you may not need the cable that we showed in the middle. And on the right-hand side, that's what the charge amplifier look like, or yours might look a little different from the two designs that are two of PCB's designs that I showed there on the right-hand side. And the output of the charge amplifier is either in millivolts per picocoulomb or microamps per picocoulomb. What is the sensitivity of the system? To figure that out, we simply multiply. So here's an example with a PCB EX619A11 accelerometer, high temp differential charge accelerometer with a sensitivity, nominal sensitivity of 50 picocoulombs per G, and a PCB charge amplifier, differential charge amplifier EX682A40 has a conversion factor of 10 millivolts per picocoulomb. So as you see on the bottom, it's very simple. We multiply those two values, 50 picocoulombs per G by 10 millivolts per picocoulomb, to come out with 500 millivolts per G. And if you're into units conversion, the picocoulomb units wind up canceling out because one is in the numerator and the other is in the denominator of the fraction. So they're gone, and you wind up with 500 millivolts per G. I just wanted to sound smart there. Numerator and denominator. I don't think I've said that since maybe college or even high school. Anyway, how can we test? So how can we troubleshoot these sensors, and how can we test them to make sure that our vibration measurements are correct? Well, best way to do it is with the aforementioned portable vibration shaker table, which provides mechanical excitation for the transducer, which you see in this video. In the video, I actually have a 4 to 20 milliamp vibration sensor mounted, but I just wanted to mount something big. That's an intrinsically safe, hazardous area approved 4 to 20 milliamp vibration sensor. But anyway, a vibration shaker table, no matter which type you use, can, of course, offer, well, not no matter which type you use, but it offers acceleration, velocity, and displacement scaling in metric or English, peak or RMS. And of course, it can vary the frequency of vibration in hertz or cycles per minute. This is another little hidden video to show the operation of the shaker table without a sensor attached, with the amplitude on the left side of the screen. You probably have to squint at it, and the speed or frequency on the right-hand side of the screen. But a portable shaker table helps us compare known vibration levels versus measured vibration levels in the monitoring system. So people always ask me, what speed do you like to test at? I like to test at machine running speed. The most common vibration issues occur at 1 and 2 times machine running speed. So that's a great place to start to make sure that your system is working correctly at those specific speeds. With the shaker table, we can of course drive the sensor to the alert and alarm level and wait out the time delays. And I went to a seminar one time where it was about temperature sensor calibration, and the presenter he actually made the point. He said, what do we really care about in a temperature measurement? Care about the alert or the alarm triggering at the right time. Do we necessarily care about the calibration of the temperature sensor, or just that the alarm works? And so that was kind of the point that he made. And you can make a similar point in this system. If the transducer's output is a little high, do we really care? Not if the charge amplifier's output is a little bit low. So it's a matter of making sure that the system does what you expect it to do, which is trigger at the right time to prevent a catastrophic failure. So it's just a thought. A lot of people get tied up in calibrating charge amplifiers or charge sensors, but what a portable calibrator allows you to do is make sure that the whole system is working correctly. And in the end, that's what we're expecting of our system. We're expecting it to shut down the gas turbine, or at least provide a warning if the vibration is getting to a point where it's out of control and becoming dangerous. This is just an example of the typical application, but in this case, the customer was using proximity probes. This was courtesy of Indonesia Power, actually. Very kind of them to share these real-life application photos. I don't want to get too into it because it's proximity probes, and it's not differential charge, which we're going to get into in a second. But this is the idea. You can bring the shaker table out to the gas turbine during an outage, not while it's running. It's so hot. And perform these loop checks. Call it a loop check. So in this case, they were loop checking a proximity probe, but you could do the same thing with high temp differential charge accelerometers. Now, there are some specifics that we have to worry about when we are troubleshooting the high temp differential charge accelerometers. And the first one is mounting, because these are not as easy to mount as a typical route-based accelerometer that could be like magnetically mounted or stud mounted with one stud. It's really easy to do. These sensors either have 3 or more commonly 4 mounting bolts. The good news is the portable vibration calibrators that are offered through the Modal Shop and PCB Piezotronics have supplied mounting pads that cover the most popular bolt patterns for gas turbines. So it covers the sensors that are OEM sensors that are manufactured by the most popular companies, PCB, of course, but also Vibrometer, Bentley Nevada, and B&K, specifically for gas turbines. I will point out we have, so there's a difference between using a multi-hole mounting plate like this, which is very convenient, and using a customized mounting plate that's just big enough to handle the sensor that you want to test. These plates are great for loop checks, and they can work for calibration too, but they're a little heavier than they need to be because they're built to accommodate the 6 most popular bolt patterns out there, which is going to cover 98% of the sensors that are in the market that are installed on gas turbines. If you're interested in doing loop checks, these are perfectly fine. If you are a calibration lab and you need to push these differential charge sensors to their maximum high frequency response, adding mass is going to be counterintuitive of that. So I would recommend customized lightweight plates if you need to take these sensors to their absolute maximum high frequency response, which is anywhere from, well, we'll call it 2 kilohertz to 5 kilohertz. A lot of end users aren't really interested in that. They want to know if the system works at running speed or 2 times running speed, and they don't need to take it to 2, 3, 4, 5 kilohertz. These types of pads are going to add mass, so you're going to wind up with going a little bit out of tolerance as you approach the extreme high frequency response of the transducer. So again, if you need to take it that high, there are customized pads available that will cut down on the mass and allow you to calibrate the sensor all the way to the extreme high frequency point. But these pads here that are supplied to the calibrator are really convenient. And again, they cover most of the sensors in the marketplace, and they're tapped as well. They're all the bolt patterns are tapped for the supplied mounting bolts that come with the sensors. So it's really plug and play. Just one of 2 mounting pads, choose the one that mates up with the bolt pattern, and away you go. Here's a quick example of comparison method. Is nothing fancy. It's just what's the known vibration on the screen versus the measured vibration on data acquisition. So just an example of what you would do with a very simple data acquisition unit. Obviously, customers have more advanced data acquisition methods than this. They'll have overall vibration levels off the DCS, especially if they convert the signal to a 4 to 20 milliamp DC output. They'll have vibration alarms. They'll have dynamic signal inputs. It all depends what data acquisition systems use in the field. And this is just a really simple example. So in this example, my first vibration alert is at a 1/2 inch per second peak. So once my alarm, there it goes. I was a little slow there, but the alert light triggered. The vibration alarm is at 1 inch per second. Let me try to get ahead of it here. Once you see this vibration alarm read above 1 inch per second, we have a 3-second time delay, 2 and 1, and boom, there it goes. So in essence, that's how you test vibration alarms in the field, whether it's differential charge or a prox probe or regular accelerometer. Drive the sensor with a known vibration input at a speed that makes sense, usually running speed, and to the alarm state, wait out the time delays, and make sure that the logic trips. Yeah, specific to gas turbine accelerometers, they're really expensive, first of all. I'm sure most of you know that. What if the measured vibration and the known vibration that you get from the shaker table don't match up? What if the value is incorrect? Well, then we can test certain elements of the system to find out where the error is. And I always recommend that people start with testing the accelerometer and the charge amplifier as a system to start off. Because if, and this is how you do that. So the reason I test the accelerometer and the charge amplifier as a system to begin with, easy to do. You don't have to disconnect anything. All you have, well, you do. You have to disconnect the charge amplifier from data acquisition and connect it to a voltmeter. It's easy to do. You can use a voltmeter. If the shaker table has a sensitivity display, you can use that. But there's a lot of ways to do it, and it's a minimal amount of connecting and disconnecting. Like, you don't have to disconnect the charge sensor from the charge amplifier. So that's where I start. And if the charge accelerometer and the charge amplifier combined work out to produce the right voltage or current, then you know the problem is in data acquisition. Could be a scaling error, could be a noise error, could be an alarm setting that somebody made a mistake with and didn't correct. You know you can move downstream from the sensor and charge amp if they check out okay. So remember the previous slide, the sensitivity of this system, sensor and charge amp, is the accelerometer's output in picocoulombs per G times the charge amplifier output in millivolts per picocoulomb. So our previous example was 500 millivolts per G. So you have to pay attention to whether or not the charge amplifier has an AC voltage or AC current output, just so you set your voltage, your multimeter in the right scale. Now, I would suggest if you're using a multimeter like I have on the screen there, like a Fluke 87 or some, I don't know which Fluke model it is, but I would recommend if you're using a multimeter to shake the accelerometer in RMS scale. That way we don't have to do any math. That comes up all the time, peak versus RMS. DVMs measure in voltage or current RMS. So let's just shake in RMS, and then we don't have to do any math or worry about converting from peak to RMS. So if we shake at 1 inch per second RMS or 10 millimeters per second RMS, it makes the math really easy. You can also, that's just velocity. If the output of your charge amplifier is in acceleration, then you would choose 1 G RMS or 10 meters per second squared RMS. And then again, we have really, really easy math in that case where we're actually going to see the sensitivity of the system on the screen if we're shaking at 1 G or 1 inch per second RMS. So that way we can easily figure out if the system output is correct. Okay. The other way to do it, you don't want to worry about peak and RMS and all that stuff. You can use a shaker with a sensitivity display, and that will perform the calculation for you. And then you don't, if you use a shaker with a sensitivity display, you don't have to worry about the amplitude either, because you could be at 1 or 1.25 or 2 or whatever value you want. The shaker is going to calculate the sensitivity of the system for you so you can compare it with what you're expecting. It doesn't matter the amplitude. If you use a voltmeter, that's where I suggest using 1 inch per second or something that makes the math easier on yourself, because you have to divide by that value to get the sensitivity of the system. Okay. Now, what if our system is showing the wrong overall sensitivity, like the charge accelerometer connected to the charge amplifier, and we're not getting the right number? Well, now we need to figure out which element of the system is failing. Is it the accelerometer? Is it the cable in between? Or is it the charge amplifier? So, and if the accelerometer has integral cable, then I guess there's only 2 options: it's accelerometer with its integral cable or the charge amplifier. So this is where I would suggest isolating the accelerometer itself and measuring the output in picocoulombs using a known good charge amplifier or a shaker table that has a sensitivity display with a built-in calibrated charge amplifier, which, of course we offer. I'm trying not to be too salesy, but we do have that. The key here is you can't just measure it with a DVM or a DMM, because the output is in picocoulombs. So you're not going to be able to measure it. So we need some sort of known good charge amplifier. If you happen to have a spare in the INC shop and it's good and it's been calibrated, we can use that and connect it to the accelerometer that's been taken off the gas turbine. Or you can use a shaker table, like I said, with a built-in calibrated charge amplifier. So that way you can isolate the transducer and figure out the output in picocoulombs per G. In this case here, I was testing a 100 picocoulomb per G sensor. You can see that the sensitivity is 97.6. The tolerance on it was plus or minus 5%. So anything from 95 to 105 passes. That's probably a good point. You're not going to get exactly right on the number. There's going to be a tolerance, usually 5%, and so you have to make sure that you're not failing sensors just because they don't land specifically on the nominal sensitivity. There is a tolerance there. So in my case, anything from 95 to 105 passed calibration. So this sensor was good. If I wasn't getting the right output from the charge amplifier, then I would know that the issue is with my charge amplifier. And you might be able to fix that because it's a lot easier to fix something like that than accelerometer. So that kind of leads me into my next question. People always ask me, if a vibration sensor is out of tolerance, can you fix it? Generally, no. Vibration sensors are all, in industrial markets, vibration sensors are all hermetically sealed. So if you're going to fix it, you need to cut it open again. And that is very cost prohibitive. In most cases, it is more practical to just replace the sensor, because opening up a hermetically sealed unit, adjusting the crystal stack on the inside, tightening the preload, or make any types of adjustments is going to be very costly. And then sealing it again is going to be very costly, if it can even be done. It's debatable. It depends upon the design whether or not you could even do it. Or are you going to damage the internals of the transducer just trying to open it up? So in general, no. A sensor, if that is the source of the failure, it needs to be replaced. Sorry. However, electronics can be adjusted. It's possible. It's much easier to adjust electronics or data acquisition than it is to make an adjustment to a hermetically sealed accelerometer. So it is possible, if the source of error is the charge amplifier, that can be repaired. It kind of depends upon the vendor and the charge amplifier itself. But it's certainly easier to repair that type of device, although it might need to be replaced. The picture here, I just want to point out, making adjustments within data acquisition, it can be a slippery slope. Okay, let's say you find that everything about your charge accelerometer system has drifted low, and your output of the system, you're expecting 500 and you're only getting 400. So you could theoretically make an adjustment to data acquisition and type in a different number as the expected input sensitivity, and you would have a correct measurement. But that can be really tricky, because what can happen is the next time you have an outage and you take everything apart and hook it all back up together, and you might not connect the same sensor and charge amplifier to that channel, and you might forget that someone made an adjustment to the sensitivity on that channel. So that's where, in my experience with customers, they tend to want to just replace instrumentation if the sensitivity is drifted too low or too high, rather than mess with the settings. But everyone's situation is different. If you have a good way of documenting that and you feel safe about it, then you can, of course, adjust, like I did here on an Emerson's CSI 2130. I was just showing in this video how to adjust the input sensitivity for a 90 millivolt per G transducer instead of 100 millivolt per G transducer. So that's what I have on the screen there. So that's my 2 cents on that topic. Oh, yeah, forgot about this slide. These are some of the other common reasons for error, and spiking and false trips are 2 of the biggest ones. We talked about scaling, programming, and wiring, etc. Spiking is really tough to troubleshoot if it's a grounding issue. I've had a lot of customers tell me about trying to troubleshoot a ground fault issue, ground loop issue, I should say. I had a customer who used the wrong screws on the back end of a bunch of signal conditioning proximeters in a cabinet, and they were having a spiking issue because those proximeters weren't properly grounded. It can be really difficult. So one way to possibly alleviate a spiking issue is to set up time delays in data acquisition. So a time delay is set up so that before you shut down or sound the alarm on a piece of rotating machinery, data acquisition has to experience or measure a high vibration level for a certain amount of time before it triggers that alarm. So in the example I showed earlier, I had 3-second time delays. My data acquisition system had to experience vibration greater than 1 inch per second for 3 seconds before it would trigger the shutdown alarm. And you could use 10 seconds or something even longer. And that way you don't get unexpected shutdowns due to ground loops or spiking or false trips or transient events, things like that. So time delays are a great way to make sure that the machinery is experiencing a real level of vibration for a fairly significant period of time before you shut it down, just in case you get any noise or ground loop induced spiking. Yeah, so that's some of the common faults. Yeah, we'll move on to the next one. Yeah, just a quick, I guess this is a quick sales pitch for the shaker table, but as we mentioned, shaker table is available for sale or rent through the Modal Shop and through PCB Piezotronics. Can also troubleshoot proximity probes, and yeah, that's just a close-up look at our proximity probe. Mounting bracket, I don't want to get too salesy. Okay, just wanted to point out that our previous series of webinars occurred in November and December of 2020. They are available through our YouTube channel. Just search on Modal Shop. And you can actually, if you are a real glutton for punishment, you can watch all 6 in a row if you wanted. That's going to be a lot of material. You might have to pace yourself. But it's sorted by playlist, so you can actually click on the playlists and see this series of 6. So we did PCB, high temperature. You know, we kind of went through the technical, more of the technical behind PCB's high temperature on turbine accelerometers in our first one. I did a troubleshooting vibration shutdown alarms presentation. We did noise exposure, we did ground fault monitoring, human vibration, and the importance of accelerometer and pressure sensor calibration, specifically combustion dynamics, combustion instability, pressure sensor calibration. I thought that was really cool. I didn't know much about that myself, so I enjoyed it. This was kind of I thought this was appropriate. I mean, this is another kind of quick, I guess it's a cheap plug really, but the first presentation that we did on PCB's high temp differential charge gas turbine accelerometers talked about 3 of the 5 points on the screen here. You didn't need anyone like myself to tell you about cost savings and delivery and non-technical things. So we wanted to go over the calibration of these transducers and how with frequency response sweep calibration, PCB has an advantage over other vendors. PCB has a very innovative UHT12 sensing element that helps eliminate the spiking that I mentioned earlier, spiking in the signal that causes false trips. And finally, all of the sensors are hazardous area approved. And this is our YouTube channel. So if you want to take a look at that previous series of webinars, just go to our YouTube channel and then you can click the playlist. It'll pop up on the right side of the screen. So here's the 6 presentations and how long we blabbered for. And so that this is a good way to review that previous content. And with that, one more time, through the next week's webinar is liquid level on February 4th. Previous webinar was digital accelerometer, turning your phone into a vibration analyzer. February 11th was high temp is going to be combustion dynamics pressure probes. it's kind of my Achilles heel of product knowledge, so I'm looking forward to that one. I have a lot of Achilles heels of product knowledge. Wireless vibration on February 18th. February 25th is 4 to 20 milliamp plug and play with your DCS. And March 4th is vibration analyzer calibration. So you'll be stuck with me again on that last webinar. All right, thanks everybody for attending. And we'll follow up with the answers to some of the more difficult questions that stumped me for sure. And I hope you have a great rest of your day, and I hope this presentation was useful. Thanks again.